So in the first video, I talked about getting in a noisy file, filtering it out, multiplying it up, doing some math on it and multiplying it up. And then we talked about the modulate block, how this gives you 250 kilohertz. When FM is set to 1 volt, you get 250 kilohertz out, and then we're amplitude modulating with the signal in from the file. And hopefully, like in 228, you had some exposure to amplitude modulation, but what this modulate block does is it basically takes this waveform and multiplies the 250 kilohertz signal by this waveform. So let's look at what the math is for that, and we'll look at this one multiplies the waveform and sends it out through the channel, and then it gets received by the receiver and it gets multiplied again by the same frequency. And let's see why that happens. Let's do a touch of math. So the trig identity we're going to use is this trig identity. There's some other ones that you can use and you get the same result, any of these multiplying identities, but this one is cosine in, cosine out, so it's easy to use, so we'll use this one. So in this case, voice is the message that's input in the WAV file is actually voice, and that's 200, 300, 500 hertz, and what we're multiplying it by is that that FM, remember the FM input's 1 volt and mark is 250 kilohertz, so we're multiplying it by multiplying the voice, the hundreds or whatever it is, signal by your 250 kilohertz, and that's what comes out of the modulate block. So this is happening inside the modulate block. And the block in a circuit that does that is called a mixer. So a mixer just multiplies two signals. So this has some frequency, we'll call it omega 1T, or we'll call it omega voice T, and we'll call this omega carry. So this is really hard to see. Make this a little bit prettier. So we'll call this, we'll call that the signal, and we'll call this the carrier. Okay. The frequency that you bring things up to, that's usually called the carrier. And voice, that's your actual signal that you're trying to transmit. So if you have cosine of omega, your signal, and you multiply that by cosine of your carrier, you just get exactly your 1/2 cosine, the difference in the frequencies. So omega S minus omega C times T plus cosine frequency of the signal plus the frequency of the carrier times T. Okay, so that is actually what comes out of the modulate block and gets transmitted. Okay, so now we've got to here with the signal. And it goes through the channel, and again, this is a voltage follower, so the same signal that comes out here comes into the receiver. And if you notice on the receiver, your signal comes in from the channel, and it just gets multiplied by 250 kilohertz again to come out here. You'd say, well, wait a minute, to transmit the signal, I took the original signal and multiplied it by 250 kilohertz, so shouldn't I divide it by 250 kilohertz? Well, trig magic happens, and let's see what happens here. So this is the signal that we've transmitted right here And we get this on the receive side. So this is the transmit side. That's what comes out of the transmitter. And then on the receive side, what happens is you receive this signal. You receive this signal, and then you multiply it by the carrier frequency again. So remember that we're on the receive side, we're putting it through another modulate block with the same carrier frequency, that same high frequency. Just a comment up here, sorry. When you transmit this signal, what you get is whatever your carrier frequency is, and in our case it was 250 kilohertz. 250 kilohertz. What you get is two signals on either side, and the difference here, so you can see that the difference here is the difference between your carrier frequency and your signal. So this is actually the distance. If you zoom in, this distance right here is just the frequency of your signal. So it's offset from your carrier frequency. It's offset on either side by your signal frequency. So that's what gets transmitted. Then you get it on the receiver side, and you multiply it by cosine of the carrier. So let's multiply this out. You've got the 1/2 out front, and then you have this times this term. I'm just distributing it. So you've got cosine omega s minus omega c times t times this term right here. And if you remember your trig identity, let's bring it down just so it's move it out of the way in a minute, but that's our trig identity. So if we multiply this times this term, you get another 1/2, and you have cosine of this frequency now. Since you're multiplying this times this, you have this frequency, that's your x now, minus whatever you're multiplying by. That gives you the first term of this frequency times this frequency, and then you have, so that's the difference term, and then in this identity you also have your x plus y, and this is, again, this is your x, omega s minus omega c plus omega c times t. That's this times the first term. Then you actually have a second term, which is this times this. And again, using this trig identity, you get 1/2 cosine. Again, this is your x now. So you've got omega s plus omega c. And then you've got minus omega c t plus, that's the first term of multiplying, and then you've got, so you just did the difference term, now we do the summing term, and you have cosine of s plus, oops, sorry. Sorry, we're over here. Okay, omega c, and then we've got this, since this summing term, now you have another omega c. Close that, and then close this other bracket. And so on the receive side, when you mix or put it through the modulate block, you get that. Okay, let's do a little bit more math on this. Move this out of the way. Just move it down. Let's move it down farther. Okay. So then we have this, and if we clean this up a little bit, let's keep the 1/2 out front. have 1/2. You look at this, you get cosine of your signal minus 2 omega c t plus cosine omega s t, which is your original signal that you want to get back. And this also had a 1/2 in front of it, so I'll just do a plus, and then you have cosine omega s t, because the c's cancel out, and then you have a plus cosine omega s plus 2 omega c. And so what's interesting here is that you actually have got two terms, which is your original signal, the voice signal that you're trying to transmit. So if you look up here, what we had is we had our voice, the signal that we actually wanted to transmit. And we've actually got that back right here. So looking, let's distribute this all out, and you get 1/4 times 2 cosine omega st, the signal that you want. And then both of these, you have, remember that the carrier frequency is much larger than the signal frequency. So both of these are like double the carrier frequency. So we're multiplying by 250 kilohertz. So this is actually close to 500 kilohertz right here. Your signal is actually at 200, 300 hertz, but this is near 500 kilohertz. So both of these are at very high frequencies. If you remember that cosine, it's an even function, is that the right word? So whether this is negative or positive, these both show up as big frequencies right here. Negative, positive value inside the parentheses. It doesn't make a difference because it's the same thing on both sides of the y-axis. So these are actually big frequencies. So big freq times t. You could put a 2 on there. So 2 times big frequencies. So what you get is you get your original signal back. My pen stopped working. Oh, it was working so well here. So you get your original signal back, but at half amplitude. So your original signal comes through, gets transmitted, but it's half the frequency. And then you have this high frequency component here. And if you look on the receiver, so now you've mixed it here, and this is just shifting it up by 1 here, subtracting 1 and shifting it up by 1. If you look at this, there's a filter right here, and this filter is a low-pass filter, so it lets the signal through, the voice signal through, the a few hundred hertz signal through, but it gets rid of the 500 kilohertz signal. And then the output here is just adjusting it. Remember that WAV files need to be, I forgot whether I said that or not, I'm sorry. WAV files, just to make sure I said that, WAV files, their voltages are always between -1 and 1. So now it comes time to dump the WAV file. I just adjusted it back so the output signal would be between -1 and 1. Okay, so I've got our transmitter that has a low frequency signal, and it mixes with a high frequency signal, which basically just shifts up your low frequency signal. This is amplitude modulation, goes through the channel, which we don't have it doing anything right now, gets to the mixer, gets multiplied by that carrier frequency again, which gives you a high frequency component that you don't want, and a low frequency component, which is your original signal. And then you filter out that high frequency component and you get your actual signal back. And then we are dumping this output signal to a WAV file, this directive, and it shows up as your radio out in your same folder. So, whoops, I changed my folder path. But if you look in your folder where you ran your simulation, you should have a new file called radiout.wav. And if you double click on that, you can listen to it and see what the message is.